Yeah. Okay, so let's go back to my slides. I don't know how many more I have. Okay, so we talked about blending, and this is how it works. Amy just brought up a very important point, though. I didn't want to share it with everyone. She said to be careful. If you do blending in Pro 2, it won't actually blend your viscosities very well. And actually, it won't even blend them, I think, if you have more than one assay. I wasn't aware of that, but if you need to do something like that, call me and I'll contact SimSci. But she has an open support case with them for a long time now on viscosity prediction from blending assays. It's not doing, and I think I read somewhere that they're using a really old API correlation to do the viscosity prediction, and they actually API doesn't even recommend that method anymore. So be careful if you do need to, look at viscosities. So when do you not want to blend? Okay. So we talked about how it would blend everything together and make you one set of cuts, but when do you want to just keep them separate as separate sets of pseudo components? The main thing is you want to differentiate between the properties. Like if you have a really light stream and a really heavy stream, you don't want to combine them and make one set of medium weight stream because it won't represent either of them well. So like the example I gave here is if you have a low sulfur stream and a high sulfur stream, and the blend would be like a medium sulfur stream. So it doesn't really make sense. It won't represent your low sulfur or your high sulfur. The other reason is if you want to do some economic analysis, if you want to track what happens to this feed, and when it makes the products, you'll see, you'll get X dollars per barrel for this assay and then Y dollars per barrel for this assay. But if you were to blend them into one set of pseudo components, you can't keep track of that because you don't know where it came from. So those are some of the reasons why you don't want to blend. Okay, so that's the assays part. Any other questions on that? Or I know it's a bit strange if you haven't seen it before. Yes.
The refinery typically provides us with the.
Yeah, they would pay like a lot for the labs to run these assays. And I think back in the 80s, we used to have like a folder with like West Texas Sweet would have this TBP and we had like Oman Bintulu crudes. We used to have like a library of TBPs for all these well-known crudes. I don't know if we still do. Helmi, do you know? Is he still here? Oh, okay. But yeah, we used to have a big old file cabinet, and you go through, and he was like, okay, West Texas Sweet has this, and you just pull it out, and you start looking at it, and we used to plot it and see if there's anything weird in that curve. But yeah, the refineries will usually provide you with that, and then you would put it in. Mm-hmm. Okay, so we're going to talk about the column now. It's kind of a strange jump, but since if you do enter an assay, you probably will do a distillation to break it up into different products. Okay, so for Pro 2, let me just show you what it looks like in Pro 2. This is a column, distillation column, and you can have multiple feeds on any of these trays. Like here they have 3 pump arounds and 3 size strippers. So hard to control right now. Okay. And you can even have like a feed furnace. We'll talk about that. Model like a flash zone. You don't have to have a condenser or a reboiler. You could just have say if you have a liquid extraction column, you just want 2 streams going in. But for crude columns, you usually do. Let me go back to the slide. So all the stages are at equilibrium, and your reboiler is your last stage. So the way Pro 2 numbers it is condenser, if there is one, is stage 1. If not, it's the topmost tray is stage 1. And this gets to be a little, it's math. There are 5 algorithms for it to solve the distillation column. There's an inside-out algorithm. You basically have 2 matrices, one inside the other. That's why it's called inside-out. Is an inside matrix gets solved first, and then it'll come out and solve the outer matrix. And you can't do total pump arounds on that. Total pump arounds means you take all the liquids off a stage and then pump it around and feed a stage that's above it. So no liquid would go to the tray directly below. You can't do that, but you can have. There's some tricks around that. Like for example, maybe you just have like 1 mole of liquid going to the next tray to simulate that. If you have any vapor, liquid equilibrium columns like extraction or azeotropic distillation, you use this ChemDist algorithm. And these are just algorithms, like the mathematical methods that it uses to solve the column. It's not, it's not really the types of column it has. A column is just a bunch of trays that you would lay down and use to simulate your distillation. And there's a Schur method. I don't know why it's called Schur, but it uses the Newton-Raphson technique with matrix partitioning. I don't know what that means, but it's just Newton-Raphson. I think it has to do with root finding with some Taylor series. Let me show you the help. Help is pretty good in explaining the math. I think that's kind of beyond what we need to know, but it's helpful if your column is not converging and you can take a look at the results, and knowing a little bit about the math would help you. But actually, let me just go through the column, probably faster, through the context-sensitive help. Here's the algorithm. Let's see if I put it here and go to help. Did anything happen? All right. So in the help, it'll tell you what the IO inside-out algorithm does, and it says you could only decant water at the condenser. And then the Schur algorithm. This is the one that's been in Pro 2 and process. It's the old workhorse algorithm. It's always been there, and tells you what the advantages are. You could have 2 liquid phases. You could have water draws anywhere, below the condenser, whereas the IO algorithm only allows you to draw water at the condenser. Some are slower than others. VLLE use the ChemDist, and then tells you the disadvantages there. If you have an electrolytic solution and you want to do distillation there or separations, you use the electrolytes algorithm, liquid. Okay, so those are the basic. There are like 5 basic ones that you would choose from. Oops, back. Okay. Yes.
Our given design is going to determine which algorithm we use, right? Or is it you guys model it differently?
No, your design will just have you set it up a little differently. Like in terms of Pro 2, you would just lay it down and put in, if it's an existing one, you have trays or packing, you would go and do that. But the algorithm is just something that you pick to have it do the math, to calculate it. It's kind of a, how do I explain this? It's like when you give it the specifications and all these information up here, it'll take those and make equations out of it, and then it'll try to solve it. Yeah.
The design, though, is what's determining how the equation is run or how the equation is put together.
The design, you'll do it in terms of specifications, and then this, depends on the degrees of freedom of the column, you can have, X number of specifications, and it'll need to vary, like, say, duties and draw rates in order to meet the specification. So, yeah, that does come into play that way. But, like, these algorithms are just, they're just math that it uses to solve the columns. But, yes, it is dependent upon on how you set it up. But by default, it uses inside out, and then you can go and choose any of the other ones that you want to use to help it solve it. A lot of people, they just run it with inside out, and if it doesn't solve, they'll say, oh, let me try this. And it's just a mathematical method to solve, like, these matrices. So, but like the column here is just one column, right? Well, there's like the batch distillation, but we hardly ever use batch. So the design, the part in the design is in those little buttons that you would go and set it up, like what kind of condenser do I have, and I'll go over that. So these are the required inputs that you need for the column. And first time when you lay down a column and drop it off on the PFD, it'll ask you how many theoretical trays or equilibrium stages. That's what a theoretical. Sometimes people are very picky, and then if it's theoretical, it should be you should say stage, not tray. Tray is like actual. So sometimes I mix them up. I don't know. But theoretical means it's always at equilibrium, and then you need to give it a pressure profile. If you're doing tray hydraulics, it'll calculate for you, but you need to give it a lot of information. You need to tell it what kind of feeds are going in and what kind of products you want out. Then specifications, like if you want endpoint for a product, or C1 through C4 content, or RVP of a stream, or cetane index, any of those refinery inspection properties you could use as a specification. And you don't have to have these in a column. You could, but you could have condensers or coolers, reboilers or side heaters, and pump arounds. Let me show you really fast. I'm just going to put down a. So basically, you just pick a column, and then you need to give it a number of trays. So let's just say 10. And then you would give it, feed it to, say, any tray. The way you draw it doesn't really matter. Like right here is 1, 2, 3. Looks like I'm feeding on tray 5, but that's just, it's not actually that until you go inside and tell it where you're feeding it. So, and the product here, just for simplicity. So, you'll see that pressure profile is red, so I need to tell it, give it a pressure profile. It could be, overall, you could give it tray by tray. So I could say top tray pressure is, I don't know, 50 pounds or something. And then you could have pressure drop per tray, maybe like 1 pound or something. I'm just making this up as I go. Or you could give it the pressure drop for the whole column, like a big delta P, So if you say delta P is 20, then this will be 50, and this will be 70. So the pressure is higher at the bottom, so it goes up. All right. And you could also, if you do it by individual trays, then you have to do it here, like tray 1 is this, and tray 2 is this, and so on. And feeds and products. So right now, as I mentioned, like I just drew it so it feeds in the middle of the column, but it really doesn't know where I want to do it until I tell it here. So I could say feed it on tray 2 if I wanted to, but it won't change the picture. Okay, so you can feed it on any tray. And there's an option, you could actually feed it both vapor and liquid. If you do have a mixed phase stream, you could feed it both onto the tray, or you could flash it so the vapor goes to the tray above and the liquid goes to the tray that you're feeding it to. And in my case, I have, I drew out 3 products. So this will be my vapor, and then this is my liquid overhead, and then I have a bottoms. So it knows that. And then you would need to give it some estimates because the algorithms, the math that it's using, needs some initial estimates. It needs some beginning numbers to use so it could start calculating. So whatever you give it in terms of the rate will be an estimate. And if you don't change it, it'll actually fix some of these for you, and I'll show you. It has to do with the degrees of freedom. So let me go back to the slide. Oh, let me just show you really fast how to add a side exchanger or something. So I have a condenser, so it's blue. So heaters and coolers. I could, put a heater, say, on my feed tray. I'll say 5. And give it a duty. And again, this duty will be fixed until you vary it to meet a spec. So, I don't know, 500 BTUs or something. So it will also help you model heat leaks to the environment if you want to. And then you can give it all this information, like it could be an overall heat leak or heat leak from the condenser, reboiler, or heat leak per tray. And there is something called a flash zone model here. Flash zone just means you have a heater, a furnace, a fire furnace or something at that tray. And the flash zone will let you bypass that tray. You could have a liquid bypass and a vapor bypass, so that it won't treat it as another tray in your column. Let's see, pump arounds. You could set up a pump around. It's liquid. You could give it a name of the stream from which tray to which tray. And I think I have a slide that explains that. First, let me go through the condensers, and then we'll get to the pump arounds. There's 3 types of condensers. Partial means you're going to get a vapor and a liquid like the one I just drew. And then there's bubble point, so you only get a liquid product. So it's a liquid that's about to boil. It's at its boiling point. And you could have 2 types of subcool condensers. Of course, it's subcool, so it's only going to be liquid. You can fix the temperature, or you could say, X degrees below the bubble point of X degrees of subcool. If you do fix the temperature, you have to make sure it is indeed subcool, that you do have a liquid. Because if you say my overhead temperature should be 100, but at 100 degrees, that stream, you're actually going to have 2 phases, then that column will never solve. So maybe safer to say, give me 3 degrees below its bubble point. And subcooled condenser is technically not at equilibrium because it's subcooled. But Pro2 will still handle that and calculate it. And then there's 3 types of reboilers in Pro2. There's the kettle reboiler, there's a thermosiphon without baffles, and you can only use the thermosiphon ones if you run it with the IO algorithm. And then there's a thermosiphon with baffles. And I want to show you the help, because there's when you do use a thermosiphon, you actually need to add 2 equilibrium stages instead of 1. Like the kettle, it treats it as just like another stage. But thermosiphon, because of the way the liquids interact, you should use 2. Let me see if it's clear about that in the help. Go to the reboiler stage. Help. Reboiler type. Oh, okay. So this is what thermosiphon without baffle looks like. Can I drag that? No, sorry, can't drag it. If you look at it, you have a 2-phase return to the column. This will have vapor and liquid. The vapor will go to the tray above, and the liquid will come down to the bottom sump here. And then this hot liquid will actually vaporize some of this cold liquid, and then the vapor will go to the tray above. So if you look at it as a theoretical stage, here's your reboiler. This is the bottom sump, which is here. Oops, sorry, darn it, shouldn't click on it. This is the bottom sump, and then the bottom's product is the draw here. So here's your reboiler return, and this is RV. This is RF. Is that F? The reboiler feed. So that's the liquid going to the reboiler right here. And then the liquid return from the reboiler is going to the bottom sump, just like here. So you need to add 2 stages, basically. That's what I was trying to show you, to model a thermal siphon. Now, if you have what they call a once-through thermal siphon, it's mathematically, it's the same as a kettle. So you just need one theoretical stage for that one. It's called once-through thermal siphon. And then if you have a baffle at the bottom of your column, it's a little more complicated now, because then you have this overflow going to the reboiler feed sump. So you need to model it like this. But as long as you choose thermal siphon with baffle, it'll take into account all these. It's just trying to show you a graphical depiction of what it's going to calculate. Let me see how you would choose that for you. So you would come up here, and if you have one without baffle, you choose that, and with baffle, you choose that. So you could give it, you need to give it some specifications once you choose the thermal siphon reboiler.
I'm sorry, so you're saying that if you specify, say, thermosiphon without baffle, will it automatically assume that the reboiler is a certain number of trays? Or do you have to add extra trays to your column to get the number of trays?
Oh, okay. This is more for like if you're translating an existing column with a thermal siphon. Say they have, we'll have that exercise at the end, but like if they have thermal siphon reboiler on the column and you need to translate it into theoretical stages, you should add 2 for the thermal siphon. So say you have 10 trays in real life with a thermal siphon, and say the efficiency is 50%. Okay, so you would say, you would translate it to 5 theoretical trays, but then you add 2.
So, right, so on the column, you would have to add, you'd have to have 8 trays on the column, is what you're saying.
Right,
5
yeah,
trays,
and then 1 for the condenser and 2 for the thermal siphon.
So even though you specify thermosiphon, it doesn't automatically assume that that's going to take up 2 trays.
Right. Yeah, you would have to manually add the 2 trays. So like if it were a kettle, you just count it as 1. But because of the way it's the liquid sump comes into play there, and there's some more equilibrium happening because of the hot liquid coming back. So yeah, you would need to add an extra tray. Or stage, I should say, stage. If you have heaters and coolers, you could put them on any tray. If it's positive, it's heat, of course, and negative for heat sink. And the flash zone data you could provide if you have any fire heaters for a tray. And I think I showed you that a little bit, but let me show you in more detail. Heaters and coolers, and then flash zones. Oh, well, okay, I'll give it 1. 5. Yeah. And this is the, you can give it an efficiency for the heater, and then how much of the liquid you want to bypass the flash zone. Let me see if there's a diagram of the flash zone. I don't have very good tools to draw, so I didn't draw it because it was going to take me like a whole day. But the help, I think I saw something in the help that has it. Flash zone data. Flash. That's all I found. But basically, you're just specifying the amount of liquid that you're going to bypass that tray, because that tray is not really part of your column. You don't want to have any separations happening there. You just want to bypass it, so you go to the tray below. That's all it is. So when you do have a pump around, that entire zone of, where the liquid is drawn and then it's cooled and it's pumped back, say you have 4 trays there. Well, on those 4 trays, you're going to have about the same liquid composition, because there's not much separation. There's no gradient in the composition for it to do any separation. So you're going to have about the same liquid stuff. So you would just model it with 2 stages. So the bottom stage is where you draw off, and then the top stage is when you return it. So it doesn't help you much if you put trays in between. And you need to give it a rate, like how much you want to pump around, and what's the duty, the cooling duty, and how you want it returned, like you can only do 2 of the 3. If you could say, temperature coming out of my pump around cooler is X, or you could say, give it a duty and it'll calculate the temperature, okay, with the rate, of course. And then you could actually have 0 duty on that pump around, just so you can bypass some trays. You could just say, pump all the vapor from here, or half the vapor from this tray to the tray above, and bypass. Side strippers or what's the other one? Strippers or fractionators? What do they call it? Rectifiers. Sorry. Side strippers or side rectifiers can be modeled as part of your column. You actually will pick it off the side, the unit ops, by picking off side strippers. Let's see. So I did a main column there, and there is a side column. Then you would just come and lay it down, give it the number of trays. By default, it gives you 2, and you could have condenser or reboiler. Let's say I have a reboiler. Sometimes the side strippers, like this, these are steam stripped, so you won't have a reboiler, you have steam. And then what happens is when you connect them, Pro2 will merge the column, so you don't really have, like, for this case, you don't have like 4 columns to solve. It actually solves it as one huge column. And you can combine your degrees of freedom and make the number of specifications based on that. And let me show you. Let me just go in here. Actually, get rid of my stream. Let me do this one that's already been done, so I don't have to randomly pick numbers. So this one has a pressure profile. They gave it the condenser, and then the very top tray, and then tray 18, which I think is the feed tray right there, and then the bottom tray. And whatever you don't give it, it'll be linearly interpolated for the pressure drop. This condenser is actually a subcooled condenser at 110 degrees Fahrenheit. And because it is a big matrix it has to solve it, sometimes it helps to give it initial estimates. If you don't give it initial estimates, it does have initial estimate generators, and I didn't go through all that. There is actually a whole section on what initial estimate generator you should use and how you can pick the right one to help you solve your column. But again, it's all math, and hopefully, you don't have to deal with that. Unless when you do a real column and you get stuck, then you could get help from me or call the support. But there's like a whole section on there's like the chemical method, how to generate the initial estimates, refinery, and the conventional, and it just basically uses like Newton-Raphson and all those different mathematical methods to come up with an initial matrix to solve. So this one, what did they do? They changed it to a refinery. That's why it's blue, but they didn't provide anything else. Yeah.